Hey there again, physics friends. Today we are talking about the momentum principle and specifically how we can apply the momentum principle to rockets. So let's kind of think back to how we've seen conservation of momentum applied in the past. So in your previous mechanics course, maybe you've seen a problem something like this. In fact, almost certainly you've seen a problem like this. We have a block of mass capital M and a bullet or some projectile of mass little m moving rightward with some velocity. Maybe we'll call it u. We're going to have multiple velocities in this problem, so we'll call this one u. And the question might say, you want to find the velocity of the bullet and the block after the collision of the bullet and the block. So let's see, find the velocity of bullet plus block after the collision. Okay, and specifically, we might be told something like the bullet collides with the block and is embedded in the block, and then that system of bullet plus block will move to the right with a new velocity v. And let's just say that the block starts at rest. So this combination of bullet and block has a total mass of big M plus little m, the block plus the bullet mass, okay? And we want to know the velocity of the pair after the collision. Okay, so when we think about conservation of momentum, the steps that I like to keep in my mind is, number one, define your system. And whatever you define as your system, you're not allowed to change it from the before collision to the after collision. So everything that's in your system before the collision is going to have to stay as part of your system after the collision. So let's define our system to be both the bullet and the box. Okay, so we care about the momentum of the system before and the momentum after. We want to account for the momentum of both of those objects, before and after. And number two, we'll use Newton's second law in differential form, meaning the system, the momentum of the system changes in response to a net external force. Okay. And then we can work from there. We might notice, for example, that there's no external horizontal force. And since we are concerned with the horizontal motion, in particular the velocity in the horizontal direction after collision, then we can just focus on that one dimension. Now, I didn't say this ahead of time, but let's assume no friction or air resistance and so on. In other words, the dominant forces in this problem, or those forces of friction and air resistance, are negligible. Okay, well, if there's no external horizontal force, that tells us that the force in the x direction is 0, okay? Which tells us that dp system in the x direction, dt, is 0, which tells us that p system in the x direction is a constant. That means before the collision and after the collision, the momentum is the same. So this is probably familiar to you now, but if we label before and after, then Newton's second law is telling us the momentum of the system in the x direction before is equal to the momentum of the system in the x direction after. So I hope you'll allow me to get rid of some of these subscripts. They're getting awfully cumbersome. I'm just going to say P before equals P after, acknowledging that we're talking explicitly about the x direction. So what is the momentum of the system before, right? Well, we have two objects. We have the bullet moving and the box at rest. Okay, so P before is equal to the bullet moving plus the box at rest. So no momentum contribution from the box that's at rest. After the collision, we have the bullet and the block collectively moving to the right with velocity v. So we can say after the collision, we have the total mass of the system all moving together at velocity v. And at this point, we just need to solve for v. We're done with the physics. We're turning the math crank now. Okay, and actually, the individual masses do not matter in terms of the ratio of v after versus u before. All that really matters is the ratio of the masses, not their absolute values. So we can divide through by little m and get 1 over 1 plus big M over little m. So the ratio of the velocity after to before depends only on the ratio of the two masses. And we can always check our work here and look at some limiting cases. For example, if the two masses are equal, which would be weird for a bullet and a block, but if they were, then we find that v is equal to 1 over 1 plus 1, or 1/2, times the initial velocity. So the speed goes down by 2. The mass goes up by a factor of 2. The speed goes down by a factor of 2. What if the block is much, much heavier than the bullet? Well, in that case, then we would find v is much, much less than u. In other words, after the collision, this term in the denominator would be very big, so you'd have 1 over a very big number, which means that v would be much smaller than u, and that's sensible. You know, if you fire a small object into a much bigger object, the net velocity of the pair would be smaller. That matches your expectations. And then the other limiting case, what if m of the block is much smaller than m of the bullet? Well, that you can kind of think of as like a bowling ball crashing into and sticking to a ping pong ball or something along those lines. In that case, we would have 1 over 1 plus a number very close to 0. So it's basically, we basically find that the final velocity is about the same as the initial velocity, and that makes sense. A bowling ball would just barrel through a ping pong ball unscathed, and the velocity would not change much at all. Okay, so I might call this approach the use of Newton's second law or the momentum principle in differential form. Right, we're starting with an equation that's describing the derivative of momentum with respect to time. But we can look at Newton's second law a slightly different way. I mean, it's equivalent, okay? You can go from one to the other, but it kind of changes the way you think about it. So let's take a look at the other way. Okay, so let's think about it this is another way, and we'll use a term called impulse, and we'll see where this is all coming from. So we'll start in the same place with Newton's second law that tells us how the system's momentum evolves in time in response to a net force. Okay. If we think of the dp and the dt as a small delta p and delta t, then we can separate these into two terms. An incremental change in the system momentum is brought about by a net force acting for a very short amount of time. Okay. Well, what is a small differential in momentum? Well, it's the momentum at one time compared with the momentum sometime a very brief time later. So we want to compare the momentum at some later time with the momentum at the initial time. So I haven't integrated here, but rather I've just expressed a delta or a small differential in terms of the difference between the momentum at two different times. And those two different times are adjacent to each other by this amount dt, which is the same dt as on the right-hand side. So if we'd like, we can identify the left-hand side as the system's momenta, at two nearby times. And on the right-hand side, we have a quantity that we'll call impulse. So this is the impulse acting over that short time. Okay, so it's like a differential impulse. And we can think of this as the momentum principle, right? And in words, in order to change the momentum of a system, you need to provide an impulse. Okay. And this is actually really going to be a powerful way to look at problems that would have been hard to talk about in other contexts. Okay. The key here, just as in before, is once you talk about a system and define the system, you have to use the same system for both of these time periods. You can't just look at one part of the system and then drop part of it when you're talking about the later time. Okay. All mass must be accounted for. So all system mass must be accounted for at t and t plus dt. You're not allowed to just omit some of the system the second time around. Okay. In other words, we're looking at a case where the rate of change of the system mass is 0 over this time interval, although the mass might be rearranged between objects in the system. Okay? And a great example of this is rockets. So in particular, you might have a rocket that contains in it some fuel. So we'll call the rocket maybe has mass m, and inside of it, there's a little chunk of fuel, dm. And the rocket is going to expel that fuel. And as a result, the rocket will gain some velocity. Okay. So to start with, we have a total mass of m and dm together in the rocket. After expelling the rocket fuel, the rocket gets a boost to the right. The total mass of the system hasn't changed as long as we continue to include the exhaust as part of the system. So the total system mass is unchanged, it's just redistributed. In the beginning, maybe the mass and the fuel had the same velocity, and after they have different velocities, but they're still part of the system. So here we've come to the application of the momentum principle to rockets. And in particular, let's consider a rocket that has a little bit of fuel that's about to be expelled. So we'll call dm the mass of the fuel that's about to be expelled, and we'll let capital M represent the rest of the mass of the rocket. So that's all the other fuel that we're not talking about right now, plus like the body of the rocket. And let's assume that at this instant, the rocket is moving to the right at velocity v, and incidentally, all this mass dm is also, all this fuel dm is also moving along with the rocket. So this is the instant that we could label, we could say this is time t. Okay, and then we're going to consider later time, t plus dt. And at that later time, the fuel will have been expelled from the rocket. Okay, so here we have the system sometime later. We'll call it time t plus interval dt, so it's just an instant later. We have the rocket still moving to the right, although we'll have to talk about what its velocity is. And then we have some exhaust that has been shot out of the rocket. And depending on the speed of the rocket relative to the ground and the speed of the exhaust relative to the rocket, from an observer on the ground, that fuel may be moving to the right or it may be moving to the left. We don't yet know. Okay, what about the speed of the rocket? Well, let's see. It used to be v, and now we've changed our velocity by an incremental amount, dv. And what about this rocket fuel? What is its velocity relative to the ground? Well, usually what we can know about a rocket, a parameter of how good a rocket is or how much thrust it can produce, is the exhaust velocity, we'll call it u, relative to the rocket, right? So imagine pinning down a rocket on the ground, fixing it, and shooting out the fuel and measuring the exhaust velocity. So that will be like a property of the rocket. But, let me see here. That is the velocity of the fuel relative to the rocket. And here we're doing our conservation of momentum in a frame relative to the ground. So we actually need to know, we want the velocity of this little piece of mass relative to ground. Okay. So for that, we can use velocity addition, right? We know that we know the velocity of the fuel relative to the rocket, and we know the rocket velocity relative to the ground. So we can write as in vector addition the velocity of the fuel relative to the ground as the vector sum of those two. So it's whatever the rocket's velocity is plus the fuel's velocity relative to the rocket. Okay. So, for example, we could say if the rocket's moving to the right, we could say the velocity of that rocket is some scalar quantity in the plus x direction, where let's make sure we define what that means. We'll say x hat, x increases to the right. And the exhaust is launched to the left relative to the rocket. So relative to rocket, we would say that velocity of the exhaust is u, and we'll call it minus v exhaust in the x hat direction, where v exhaust is positive. Okay. So now we can start thinking about the initial and final momentum, but before we do that, we have to make sure we define our system. Okay, so our system, it's equal to the rocket plus the fuel. Okay, and specifically, we can draw that in green. We're going to include in our system that little chunk of fuel, so we also have to include that chunk of fuel in the after state, before and after. So what does our momentum look like before? So at time t, we have the system's momentum equal to the total mass of the rocket plus the fuel, all moving at velocity v. And then at some time later, the system's momentum is now numerically the same, but will be expressed in different ways, right? So we have the rocket now of mass m moving at a new velocity v plus dv, and we have the fuel mass dm moving at a known velocity relative to the ground. Okay. So we can rearrange these terms and group all of the terms that involve a v. So we have big M and dm multiplying little v, vector v, excuse me. So we'll write that out. And we have a big M times dv, and then we have dm times dv plus u. Okay. So we know that the step in momentum, dp sys, is equal to the system's momentum at the second time minus the system's momentum at the first time. Okay, and we're going to get some terms that cancel, right? For example, we have this m plus dmv, and that shows up in the second term as well, so those terms will vanish, and we're just left with m dv plus dm dv plus u. In other words, we're left with the second and third terms for the second momentum expression. Okay, and so we can expand this out. M dv plus dm u plus dm dv And notice that we have terms that are first order in small, like dm is a small quantity, dv is a small quantity, and then we have these terms that are second order in small quantities. And so, in the limit of small dt, dm is going to be small, dv is going to be small, and the product dm dv is going to be vanishingly small. So we take this to be approximately just the first two terms, and we can ignore those second order differentials. So we're in pretty good shape here, right? If we return to Newton's second law now, we have something like dp cis equals F dt, the net force dt. This is our expression of Newton's second law. And our left-hand side, we already have an expression for, right? Our dp we just derived. Okay, so we can make use of that here. We have m dv plus dmu is equal to F net dt. And we can divide through dt, so we have m dv dt plus u dm dt is equal to the net force. And remember, this net force is an external force on the system. It's not the force of the rocket pushing. This is if there's an external force on the system, then we have this equation of motion. So what is this dm dt? Well, this is the rate of mass loss from the rocket, and it's a positive quantity. Okay. How about the capital M dm dt? Okay. Well, that's the rate that the rocket mass changes in time, and that's going to be a negative quantity. In other words, the remainder of mass in the rocket's getting smaller at the expense of shooting fuel out the back. But the important point is that those two quantities are not independent, right? The rate of mass loss by the rocket is equal to the rate that the expelled mass increases. In other words, dm dt, capital M is equal to minus little dm dt. Mass lost by rocket equals mass gained by spent fuel. So that means we can re-express our Newton's second law equation up above by just writing it in terms of capital M. So we can say m dv dt, that's the same as the first term before. There should be a vector on that u, plus the u vector times minus d capital M dt is equal to the net force, like so. And finally, we basically just rewrite the same thing, but with less parentheses. And we have a governing equation for Newton's second law applied to systems whose mass doesn't change in time, but whose mass is rearranged from one component of the system to another. Sometimes you'll see this called the rocket equation. And notice that this rocket equation does allow for an external force, so it's quite general. Okay, and just to talk through each of these terms, right? Capital M is the mass of the rocket, which is decreasing in time. And it's decreasing in time at a rate dm dt. Dm dt is less than 0 because the rocket is losing mass. U is the exhaust velocity, in other words, the fuel's exhaust velocity relative to the rocket, not to the ground or not to the inertial frame, but relative to the rocket, and the rocket is accelerating. And then v in the dv dt is the rocket velocity relative to some inertial frame, say the ground, for example. And notice that we're allowing for an external force. What we're going to do next, though, is examine the case where there's no external force. In other words, you could imagine like a rocket sled that's moving horizontally without drag. Let's see what that looks like. So let's now consider the special case of the rocket equation where there's no external force, no net external force. So in that case, we can imagine, say, horizontal velocity, so we don't have to worry about the gravitational force. And if you'd like, you can put our little rocket on a sled. So give it some skis. So the normal force from the ground is going to balance the gravitational force. So we could call this a rocket sled. And as this rocket expels fuel to the left, the rocket gets propelled to the right. So we can say that the rocket equation will simplify because there's no net external force. And if there's no net external force, then the first term will equal the second term so that when they're different from each other, they equal 0. So we're left with m dv dt is equal to u dm dt, like so. Okay. So the rocket speeds up to the right at the expense of expelling fuel to the left. So we know that dv dt is going to end up a positive quantity, and we know that u is going to be pointing to the left. In other words, both sides are positive. M is a positive quantity. dv dt is a positive quantity. It points to the right. U points to the left, so it has a negative sign. And then dm dt is negative, so negative gives you positive, and this left-hand side is also positive. This quantity, u dm dt, goes by the name of thrust. Right, so this tells you how effective your rocket will be at accelerating, and it depends on two things. How quickly can you get mass out of the rocket? In other words, if you can burn fuel at a very high rate, then you're going to have a high dm dt. And if you have a very high exhaust velocity, you're going to produce a lot of momentum for your rocket. Since we are talking about one-dimensional motion, let's just write these vectors out explicitly. We can say the velocity vector is velocity is a function of time, a scalar, in the x-hat direction, and that will be in the positive x-hat direction. The rocket's always moving to the right. And then the exhaust velocity is always going to be pointing to the left relative to the rocket. So we'll give that a minus v exhaust in the x direction. So that tells us u is pointing to the left, and vex is constant. It's the exhaust speed. Speed meaning it's a magnitude, it's a positive quantity, and this is relative to the rocket. Okay, so our equation m dv dt equals u dm dt, we can write in the following way. Let's just copy that down below. We can essentially multiply through the dt's, so we have m times a differential change in the velocity equals u times a differential change in mass. But our dv is just, dv vector is just this dv scalar. And our u vector is minus v exhaust dm. And so now this becomes a separable equation where we can separate the v as a function of t terms to the left and the mass terms on the right, like so. Okay. And then now we can integrate. And so we're going to integrate this. We'll do a definite integral from some initial velocity to some final velocity, and we'll integrate the right-hand side from the initial mass to some mass at another time. And so on the left, we have v of t minus v naught, just v evaluated at those limits. And on the right-hand side, we have minus v exhaust times the natural log. So this integral here becomes the natural log of m evaluated at those two limits. And when we evaluate them at the limits, we have natural log of m of t. Now, notice that the m naught is going to be bigger than the mass of the rocket sometime later. So I'm going to actually invert these by distributing the minus sign through, which gives me v exhaust times the natural log of the starting mass minus the natural log of the mass sometime later. And we know that the difference of natural logs is equal to the natural logs of the ratio, so we can express this as v exhaust times the natural log of your starting mass divided by the mass later. Okay. So we have come to our almost to our stopping point, and we can recopy this up here. We can find that the velocity of the rocket is equal to whatever it started at plus the exhaust velocity times the natural log of m naught divided by the mass some later time. And we know that m naught is bigger than the mass later because we're losing mass of the rocket, and so we can see that v of t in fact will increase. Okay. So let's just talk through this resulting equation a little bit. Let's say you wanted to get your rocket to a very high speed very quickly in a short amount of time. Okay, well, one way you could do that is by having a very large exhaust velocity, because this term, which is the time-dependent term, grows in proportion to your exhaust velocity. So if you're a rocket engineer, there's a huge payoff in having your exhaust velocity be very high. The other thing you'll notice is that if you can make the mass of your rocket drop very quickly, in other words, if you can get a lot of your fuel out very quickly, then the denominator here gets small quickly, which means this ratio gets big quickly, which helps this natural log function grow faster in time, which in turn increases your velocity quickly in time. So if your goal is to make your rocket go fast quickly, then build a rocket that can shoot fuel out with a high exhaust speed and that can shoot a lot of fuel out very rapidly. That all seems like common sense, but this is how it gets quantified using the so-called rocket equation and momentum conservation. So we're going to pause there. We're going to come back in future videos and talk more about rockets and consider situations where we do have external forces. But for now, we'll wrap. And until next time, take care and be well.